Okay, hello everyone in a new video. So we have reached part 6 of chapter 8, which is the chapter of Newton's second law for rotation. Now in this one, before we start solving this exercise, which is exercise number 8, I want to clarify several stuff that are extremely important for us. So let me start with the following note, and I want to recall the principle of interaction. Now here suppose we have a support. So this is the support. Let me say that this is the support T, which stands for a table, and let's place on this support a solid ass. Now what are the forces that are acting on the solid ass? We know that there is a weight acting on the solid ass vertically downward like this, and other than the weight, we know that what is preventing so this is the point G. What is preventing the solid ass from falling down? We suppose that there is another force, which is a contact force in nature, and it will be acting on the solid ass at the point 8 vertically upward, which is the normal force. So till this moment, this has nothing to do with the principle of interaction. We have just stated the different forces acting on the solid ass that are given by the weight and the normal reaction due to the support of the table. So now let's recall the principle of interaction. So what does the principle of interaction states that? What does it state? Now the table T So if you want to recall the principle of interaction, it is given by when a body A exerts a force on a body B, then body B exerts a force on body A, and they satisfy a certain equation that we will recall now. So the equation is simply given by that FA on B plus FB on A is equal to 0 vector. So this is the principle of interaction. Now let's say that as the table exerts a force F, the table on S, which is said to be the normal reaction in this case. So what is the force? Let me write it between brackets. So this force is given by the force F table on S, which is given by the normal reaction on the solid S on S. Then according to the principle of interaction, S will exert a force on T, which is given by a force on T that is given by F S on T that satisfies the following relation. F T on S plus F S on T is equal to 0 vector, and we know that F T on S is given by the normal reaction. So normal reaction plus F S on T is equal to 0 vector. And here I should make it very clear that now if you suppose yourself to be the table, you will feel the action exerted by the solid S on you, but Okay, one can say that this action is due to the weight, but this is completely wrong. It's not the action due to the weight. Okay, it's coming from the weight. But why? Now notice that we have said that this force, the force N, it is the force exerted by the table on us. According to the principle of interaction, there must be another force given by Fs on T. So what is this force? If we want to solve this vectorial equation, it will be given by minus n vector after we drag this vector to the right hand side. So 0 vector minus n vector, it will be simply minus n vector. So this force that we are talking about, that the force exerted by S on T, is given by minus n. So how do we read this equation that both forces have the same line of action, opposite direction, but same magnitude? So in this case, the force that we are talking about, it will be represented at the point A because it's a contact force, which is this. So this force, Fs on T, is the one that is actually causing action on the table and not the weight. Okay, for sure, this is coming from the weight. This will be equal to the magnitude of the weight. Why? Because the weight is equal to the normal, and the normal will be equal to this. So what do I mean? If we say at equilibrium, we have that the weight vector plus the tension plus the normal vector is equal to 0, which means that W is equal to minus n, which means that in magnitude the weight is equal to the normal. So weight is equal to the normal. On the other hand, so magnitude of Fs on T is equal to the magnitude of n, but n is equal to W. So overall, the magnitude of these three forces are equal to each other. Okay? But we cannot consider the three forces acting at the same time. Okay, either we consider N and W, or we consider N with Fs on T. So we don't mix between these three. Okay? So I repeat, the force that is causing the action on T is not the weight, but the force Fs on T. So let me give another example, another famous example that is given by the tension in a string. So suppose here we have a support, and here we have a string suspended like this, and here we have a ball. And this is the point A, and this is the point G, the center of gravity of the ball. Now what are the forces acting on the solid? As we know that we have the weight which is vertically downward like this, and we have the tension along the string which is vertically upward like this. We know that at equilibrium we have T vector plus W vector is equal to 0 vector, which means that T vector is equal to minus W vector, so in magnitude that the tension is equal to the weight. But now let me consider the principle of interaction, not the equilibrium condition. Okay, so either we consider the principle of interaction or we consider the condition of equilibrium. Here we are talking about the equilibrium condition. Okay, now notice that, let me say that this is the string R. Notice that the string R and the solid S are at interaction, because the string is, let me change the labeling just in order to be more clear. Let me say that this is the string S and this is the solid or the block M. Okay, so now we can say that the string is exerting an action on the solid M, which is given by the tension. So according to the principle of interaction, the solid M will exert an action on the tension on the string, which is given by Fm on S. So we have that F exerted by S on M plus the force exerted by M on S is equal to 0 vector, and here we are talking about the principle of interaction. Okay, what does this force represent? This is the tension T. Okay, Now here, if we suppose ourselves that we were the string, we will the string, as if the string, something is pulling the string downward, which is the weight. But what is pulling the string downward, it is not the weight actually, but it is the force exerted at this point, which is due to the tension, and the tension is coming from what? From the weight. So what is causing the string to be pulled downward is this force Fm on S due to the tension. So Fm on S will be equal to the minus of the tension. Okay? So what does this equation mean? That the force exerted by the mass on the string have the same line of action of T but opposite direction and same magnitude. So it will be something like this. So this is the force F caused by M on S. Okay? Now this is the principle of interaction. So any two bodies that are in contact, the first body A will exert an action on body B, and body B will exert an opposite equal reaction to the body A. So in this case, the string and the mass M are at interaction. The solid and the table are at interaction. We can consider also another example, third example, or it's enough. These two examples are sufficient, okay? And we are more interested in this example. So now I want to explain the other thing. So this is the principle of interaction. Here we are talked about examples 1 and 2. So this is example 2 and this is example 1. Now the second remark that I want to give, the second note. Now let's get back to the moments and rotation. Suppose here we have a disk. Now what I will talk here is not related to this one, but I will combine both ideas for the coming exercise, which is important, okay? So now let's suppose that this disk has a center O, so the disk can rotate around the axis of rotation delta passing through O, and let me consider here a point A and here another point B. And let me consider here a force applied at the point B like this. This is the force F1 and this is the axis of rotation. So this is the center OA. And suppose here for some reason we have another force which is being represented like this. So this is the force F2, and suppose that this is the point of application of the force F2, which is the point C. And we are interested in calculating the moments due to F1 and F2. Let's take that this is the positive direction of rotation, and let me start with the moment of the force F1. Around the axis delta, which is given by F1 tangential, so far so good. This is the distance t. We have that this distance t is equal to the radius r. So this is r and F1 tangential. F1 will try to rotate the system in the negative direction, so it's minus F1. It's completely lying along the tangential direction. If this is the tangential direction like this, so it's completely lying along the tangential direction. So no need to project, okay? So here everything is good. Now what about the moment of the force F2? Okay, before discussing the moment of the force F2, let me refer here. I'm always saying that this distance t is the distance between the axis of rotation and the point of application of the force F2, which represents the point, the distance OP. Now we are interested in calculating the moment of the force F2 around the axis delta, which is given by F2 tangential multiplied by the distance t. Here, if we need to refer to the definition that I'm always using, which is the distance from the axis of rotation to the point of application of the force, then this distance must be according to this definition, which is given by OC. And here comes the problem, because this is completely wrong. Okay, why? This is completely wrong because the force F2 is represented in a wrong way. Okay, why? Now, first of all, let's get back to the earlier representation of a force. Whenever we need to represent a force, we need to list the properties, and the properties are based on the type of the force. So the force F2 is a contact force. Why? Because in order for it to rotate the disk, it must be in contact with the disk. Okay? So here it is clear that the representation of the force is wrong. Now the point A represents the point of contact between the force F2 and the point A. Therefore, the force F2 must be represented, the head of the force must be not on the point A, but rather the tail of the vector, which is the point C, must be represented at the point A, because this point represents the point of application between the force F2 and the disk. Okay, so representing the force F2 in this manner is not correct. This is a wrong representation of the force F2. Okay, so what do they mean by this? They mean that there is a force F2 that is trying to rotate the disk along this line of action and direction, but this doesn't mean that the point of application of the force F2 is the point A, but it's not the point C. It should be the point A because it is the point of contact between the disk and the force F2. Therefore, if this is the line of action of the force like this, then F2 must be represented in this way. This is the correct representation of the force F2 and not this one. This is wrong. Okay, this is the correct representation. So, and in this case, the point of application of the force F2 will be the point A. Now, in this case, we can get back to the moment and we say that now the distance T is equal to the distance OA and not OC, because recall that we are referring to the distance as the distance from the center of rotation to the point of application of the force. And in order to use this definition properly, we require that the forces must be represented in the correct way. Okay? Now just a direct a counter example on these two combined together, let me consider the following exercise, just to explain what I mean by so. Now suppose we have the following problem and we are just interested in representing the forces acting on the rod. Okay, so as you can see, they didn't represent any force for us. We need to represent the forces. So the trick is that to represent the forces correctly in the correct way. Okay, now first of all, we have the reaction at the point A, and as I have justified previously, the reaction at the point A is not important for us because it will determine later on during the translational equilibrium. Now what about the other forces? Suppose that the rod has a mass. So, and this is the center of gravity G of the rod. So we have the weight acting like this. So the representation in this case of the weight is correct. So this is weight of the rod. Now we have the tension T along the string. Now, okay, here for sure we have the weight of the bucket, we have the tension here, but this we don't take into consideration because they are affecting the rod only along this string. So everything behind this red line will be ignored, and we will only consider the tension that is applied like this. So because this external system is only affecting the rod along this tension, okay? Now there is another force that is acting on the rod, which is the force due to the weight of the man. So one can say, for example, we can represent the weight like this. So this is the weight of the man, and this is the point of application G of the man. So this is G1 and G2, and now we can start to calculate the moments. So we can say that the moment, okay, let me start calculating the moment, and in particular the moment of the weight of the man. So the moment of the weight of the man is the tangential component of the weight of the man multiplied by the distance t, and here let's figure out the distance. So if you consider the distance, which is the distance between the axis of rotation and the point of application of the weight of the man, which is this distance, then the problem is said to be completely wrong. Why? Simply because this is not the force which is causing a moment on the rod. Okay? Now, as I have justified previously, that here, because we have the weight, so we have the weight like this, then there must be another normal reaction acting like this, and they cancel each other. But the man and the rod are at interaction, and according to the principle of interaction, there will be another force given by n prime, say for example like this. This force n prime, which will cause an action on the rod and which try to push it downward. So in this case, if we want to represent the force acting on the rod, because the man and the rod are being in contact, so the force must be represented at the point B. And this is not the weight, this will be the normal reaction at the point B. Due to the man, not due to the weight. Okay, it's coming from the weight of the man, but it's not the weight. It's the normal reaction at the point B coming from the weight of the man. Okay. Now, what will be the magnitude of this force? As I have justified previously, we can directly use that the magnitude of this force is given by N is equal to W, which is equal to the magnitude of the weight of the man. Okay? So, one should be very careful when representing the forces. We don't consider the weight of the man, however, but we consider the reaction exerted by the man on the rod. Okay? So, one should always consider these two notes whenever we are solving problems related to moments. So they can be summarized by the following note, that from the early beginning the force must be represented in the correct manner. So now, after considering these two notes, let's try the following attempt, which is to solve the following exercise. Now, exercise number 8, they are telling us a construction man is standing on a homogeneous wooden rod AC of length 2 meters. So we are talking now about the rod of length AC is equal to 2 meters, trying to fix the wall of a building. AC is hinged at A, so the moment we have a hinge, then we will have the reaction at the point A. AC is hinged at A to a vertical wall, while the other end of the rod is tied to a rope CD, passing over a light pulley at C. This is important. Later on, I will also explain what is meant by light pulley. This terminology is extremely important. The end of the rope carries a bucket of mass M containing concrete. So concrete is a special type of material used in construction. Now the rod AC has a weight of 500 newtons, so this is 500 newtons. And now, because the rod is homogeneous, so we suppose that the weight is acting at the center of the rod, which is like this. So let me say that this is the weight. Okay. So the magnitude of the weight of the rod is given by 500 newtons. The construction man of weight 700 newtons. So here we are talking about the man, which is 700 newtons. So this is the weight of the man. Stands at point B of the rod such that AB is equal to 1.5 meters. The system is in static equilibrium. Static means equilibrium, okay, not moving. Static means not moving. So here, if you consider the following note, that static means not moving. Now in number 1, notice the following question. Make an inventory of the forces acting on rod AC. Inventory means that we mean to investigate the forces that are acting on the rod, okay? Now this is extremely important because we need to represent the forces in the correct manner. Otherwise, everything will be wrong. And notice that here in this exercise, they have labeled points for me. So they already labeled the point B. Now later on, we will discuss why they are labeling the point D. Okay? Now, so we are interested in the forces acting on the rod. We have the reaction at A, reaction R at A. We have weight W of the rod. We have tension T in the string, say tension T1 in the string. So where's the tension T1? This is the tension T1. Now I repeat, what about the weight due to this mass? The other tension that is here, the other tension that is here, we don't take into consideration these forces because this is an external system. We are talking only about the rod. This external system interacts with the rod only via this tension, so we can simply consider only the tension T1 which connects this rod with the other system. Now there is another force that we should consider, which is the weight of the man, right? Because the man is exerting an action on the rod AC. So one of the options, one can say that the weight that we should represent is like this. On the center of gravity, so this is Wm for man, on the center of gravity of the man. And here comes the problem. If we need to calculate the moment exerted by this Wm, we should consider this distance, and this distance will be wrong because we have represented Wm in the wrong manner, so it's not correct. Okay, so actually here, what are the forces that we are concerned here? First of all, for sure, we have the weight of the man, which is vertically downward like this, but at the same time we have the normal reaction exerted by the rod on the man, which is upward. Now, according to the principle of interaction, as the rod exerts a force on the man, there will be another force exerted by the man on the rod, which represents also the normal reaction N prime, like this. This force N prime, which is actually causing a moment on the rod and not the weight, okay? And this force is a contact force, which is due to the contact between the man and the rod, and it must be represented like this. So now, the forces that are acting on the rod are the reaction, the weight of the rod, the tension in the string, and the normal reaction, not the weight of the man. It is the normal. And we are not talking about the normal reaction of the rod on the man. We are talking the normal reaction of the man on the rod due to the principle of interaction. Okay? So now, for the first time, it seems to be a bit complicated. But now we have faced this type of tricks, so whenever we face it again, we must use the same implementation that I have used here. And the normal and due to the man on the rod. And here we can write that N is equal to Wm is equal to 700 newtons. So this is the correct way to deal with this problem, okay? Other than that is considered to be completely wrong. Now in number 2, they are telling us use now the condition of rotational equilibrium to determine the tension in the rope. Now everything would be straightforward. We need to use the condition of rotational equilibrium, and for this reason we need to calculate the moment of each force exerted on the rod. Let's start by the moment of the reaction, which is directly 0, because line of action of R is passes through delta. Because we suppose that the rod will have the ability to rotate around the axis delta hinged at the point A. Now we need to calculate the moment of the weight around the axis delta, which is given by the weight tangential multiplied by d. D is the distance between the point of application of the weight and the axis of rotation. Because this rod is homogeneous, so this distance, which is the center of gravity, will be half the length of the rod, which is given by 2 divided by 1, which is equal to 1 meters. Now the tangential component of W, if you consider that this is the positive direction of rotation, so W will try to rotate in the negative direction, so it's minus W. And if you consider the radial direction, then this is the tangential, which is completely vertical, and W is vertical, so they are parallel to each other, so no need for the cosine. So in this case, the moment of the weight around the axis delta will be simply minus W multiplied by D. The weight of the rod is given by 500, so this is equal to minus 500 multiplied by 1, which is equal to minus 500 Newton meter. So the moment of the weight of the rod around the axis delta is given by minus 500 Newtons meter. Now let's move to the other forces. So we are done with this, and we are done with this. Now at the moment due to the normal reaction N, so I repeat, here it's a bit confusing. We are not considering the normal reaction exerted by the rod on the man, but rather the force exerted by the man on the rod. So we are talking about the moment of N around the axis delta. So usually we call this force to be N prime, but I'm calling it to be N, which is equal to N tangential multiplied by the distance D. D is the distance between the point of application of this force, which is the point B, and the axis of rotation, which is A. And in this case AB, so notice that they are specific, and they are giving me that the value of AB is given by 1.5 meters. And the tangential component of the normal, notice that the normal will try to rotate the system in the negative direction, so it's minus. And its magnitude N, and because it's okay, so this is the tangential direction, and this is the radial direction. So it's completely, this is the radial direction, this is the tangential direction. It's completely lying along the tangential direction, so no need for the cosine. The moment of N around the axis delta will be given by minus N multiplied by D. The value of the normal is equal to the value of the weight of the man, which is given by 700. So minus 700 multiplied by the distance D, which is given by AB, which is 1.5, and this is given minus 1050 newtons meter. So the moment exerted by the normal on the axis of rotation delta is given by minus 1050 Newton meter. Now recall that we are interested in determining the tension of the rope, so the moment must be expressed in terms of the tension. So let me erase everything. So the moment around the tangent of the tangent T1 around the axis delta is given by T1 tangential multiplied by D. D is the distance from the axis of rotation to the point of application of T1, which is given by AC. In this case, AC is equal to 2. Now T1 tangential is equal to either plus or minus. Notice that T1 will try to rotate the system in the positive direction, because to cancel the effect of these two to be at equilibrium, multiplied by its magnitude, which is T1, multiplied by the cosine of the angle between T1 and the tangential direction. This is the radial direction, this is the tangential direction. So if this is 30 degrees, then this angle will be 60 degrees. Now the moment of the tangent T1 over delta will be given by T1 cosine 60 multiplied by the distance T. T1 is given by, okay, T1 must be kept as an unknown. Cosine 60 is given by half, and the distance T is given by AC, which is equal to 2. So this is equal to T1. Now we are ready to use the rotational equilibrium in order to determine the magnitude of T1. So let's say at rotational equilibrium, so the sum of moments around the axis delta is equal to 0. We have the moment due to the tension T1 around delta plus the moment of the reaction R around delta plus the moment of the weight around delta plus the moment of the normal reaction around delta equal to 0. And now this is given by T1 because we have proved that this is equal to this. This is 0, and this is given by minus 500 the weight, and the normal is given by minus 1050. So minus 500 minus 1050 is equal to 0. So T1 is equal to 500 plus 10,050, which is equal to 1550, because everything previously is expressed in the SI, so the value of T1 will be in the SI, which is in newtons. So the value of the tension T1 is given by 1550 newtons. Okay. Let's proceed. Now they are telling us to deduce the mass of the bucket M, and by deduce it means that we notice the previous part. In the previous part we have determined the value of the tension. Now notice that if this is the tension T1, so here we have another tension like this. This tension will be equal to this tension because the string is inextensible. So T1 prime will be equal to T1 because the string is inextensible. But the thing is that now here we'll have another tension, and here we will have another tension. Now this tension is equal to this tension, but the reason is not an extensible string. However, because the pulley is of light, because it is a light pulley. So in order, now let me repeat. Here we have the tension T1, here we have another tension. So here we have another tension like this, and here we have another tension like this. This tension, as we used to say previously, that this tension will be transmitted equally along the pulley, and it will be equal to the tension here, which is acting vertically upward, and the weight here will be acting like this. This tension will be equal to this tension, and not because only the string is inextensible, but also the pulley is light, very lightweight. So now we need to consider the forces acting on the bucket, because we need to deduce the mass. We have the weight, which is acting vertically downward like this, and we have the tension here. So let's say that this is T1 prime. So at equilibrium, we have that W plus tension T1 prime is equal to 0 vector, which means W is equal to minus T1 vector. So in magnitude, we have that the weight is equal to T1 prime, but T1 prime is equal to T1 because, or let me say, inextensible string plus light pulley. Now yet I didn't explain what is meant by light pulley, or okay, so it is massless. Later on I will clarify the importance of the statement. So now in this case the weight is equal to 1550 newtons. This is, we are talking about the weight of the bucket. So in this case the mass is given by 1550 divided by 10, which is equal to 155 kilograms. So the mass of the bucket is given by capital M, 155 kilograms. Now in number 4 they are asking me to use the condition of translational equilibrium to determine the force exerted by the hinge on the rod A at A magnitude and direction. So now we will use translational equilibrium and say at equilibrium so this is the positive x-axis, this is the positive y-axis. Now I repeat what forces we will consider acting on the rod. We will consider only the tension T1, the normal, the weight, and the reaction R. The tension T1 prime and W and all other forces, for example here you can say that we have a force, here you have a force, here you have a force. All of these forces are not important for the rod, because why? Only the external system interacts with the rod at the point A, and at the point C. For this reason we have represented the tension T1 and the reaction at the point A. Therefore we have the reaction R plus the weight plus the normal reaction plus the tension T1, which is equal to 0 vector. And this is a vectorial equation. We need to project it twice, one along the x-axis, one along the y-axis, putting in mind that we are interested in determining R. So projection along the x-axis. Now let me project aside the forces. We have R given by Rx and Ry. We have the weight, which is given by Wx is equal to 0 and Wy is equal to minus W, because it's completely vertically downward. As for Nx will be 0 and Ny will be minus N. And what about the tension? We have the tension T1. T1x, it is acting in the positive direction, so it's plus T1 multiplied by cosine 30. As for the y direction, it will be T1y. So it is acting along the positive direction, so plus T1 multiplied by the cosine 60. So now we drop down the vector quantity. Each vector quantity will carry the label x. So this is Rx plus Wx plus Nx plus T1x is equal to 0. Now Rx is unknown. Plus 0 plus 0. Okay, plus T1 cosine 30. So in this case Rx will be given by minus T1 cosine 30, which is equal to minus 1550 multiplied by radical 3 over 2. On the calculator the value of Rx and the SR will be given by minus 1342.34 in newtons. Now as for Ry, projection along the y-axis, drop down vector quantities, Ry plus Wy plus Ny plus T1y is equal to 0, and we are interested in determining Ry. So Ry, Wy is given by minus W minus n plus t1y, which is given by t1 cosine 60 equal to 0. So ry is equal to w plus n minus t1 cosine 60. The weight of the rod is given by 500 newtons. The normal is given by 700 minus the tension T1, which is given by 1550 multiplied by half, which is cosine 60. Now on the calculator this is equal to 425 newtons. Then in the vector notation, R is given by Rxi plus Ryj, which is equal to minus 1342.34 I plus 425J. Now if you want to calculate the magnitude, because they are asking me here about the magnitude and direction, so R is equal to square root of Rx square plus Ry square, and you can replace the values here. So we have minus 1342.34 to the power 2 plus 425 to the power 2, and you can calculate this in newtons. As for the direction, it's sufficient to calculate tangent theta, which is equal to Ry divided by Rx, and it's given by 425 divided by minus 1342.34, which is equal to minus 0.32. So in this case, if we perform shift tangent on the calculator, it will be given by minus 17.5 degrees. Let me check again. Yes, this is it. Okay. Now suppose that we want to represent the vector. So okay, probably I will keep the representation for another time. But here just also a side remark that the values of Rx and Ry in such cases may be positive or negative, independent, because they represent components and not magnitudes. Okay, so that's it for me in this video, guys. In the next part we'll complete solving exercises on this chapter.